All right, welcome everybody. So sorry about the short notice this morning. Just some minor speed bumps here in the semester. What we're going to take a look at today is a continuation of the harmonic oscillator stuff that we talked about on Monday. I had planned to do SIR model in class today and then delay the harmonic oscillator stuff till Friday. I'm going to go ahead and do the harmonic oscillator wrap up today. And then I'm going to wait to talk about SIR until Monday when we're back face-to-face in class together. What I'll do this Friday is upload a video that is introducing us to the next module, which is eigenvalue methods. So I'll upload that video for you to take a look at. And then we'll talk about SIR on Monday. I may have to switch around some due dates for Module 5, but we'll cross that bridge when we get there. The skills quiz that's due today is still due today. In fact, I'm going to go over with you here in this video. So you should go ahead and grade the skill quiz based on what we talk about today, and then upload your solutions to Canvas later today. I'll post the skills quiz answer key as well, so you can look back at it. But please post those later today, and I'll take a look at those and enter the grades. So let's actually start there before we get into the harmonic oscillator stuff. So this is the today's skill quiz. The first question on the skill quiz was asking you to find all the equilibrium points or critical points for the nonlinear system that's shown here. And there are 2 points for this question. What I will suggest that you do is give yourself a half point for each of these equilibrium points that you found. So a half point for each of the equilibrium points that you found here. Now, you do not have to have shown me the graph. I just did the graph to reinforce some of the topics we discussed in class. So a half point for each of the equilibrium points. All right, for problem number 2, you are converting this third order differential equation into a first order system of 3 equations. You can either give me the system form, which we have right here. So this is the system form. That's a perfectly acceptable answer. Or you can give it to me in the vector / matrix form. So either the boxed answer here or this you can give me as the answer. So this is worth 2 points. Give yourself 1 point of credit if you got the first 2 equations correct, and then give yourself the final point of credit if you got this third equation correct. The third equation is where most of the difficulty comes in, but give yourself half credit if you get the first 2, and then the final point of credit if you were able to get the last row correct. Or if you wrote it in vector form, give yourself 2 points if the first 2 rows of your solution are correct, and give yourself the full value if the third row of your solution is correct. All right, on to problem number 3. So in this problem, you were tasked with looking at a phase portrait here. So this is a phase plot of a system, and you were asked to connect it with component plots. So which one goes with which? Well, I'm just going to point out a couple of ways I think about this. You could have thought about it slightly differently, but let's start with on curve A, or on this component plot. You can see that both the X and Y component, which I don't know which one's X and which one's Y yet, but I know that both of these pass through the origin. And if you go up here and look in the phase plot, there's only one of the 2 solution trajectories that passes through 0, 0, and that is the green trajectory here. So this green trajectory must have the component plots here. So we called that curve A, so this must be curve A. Which means this must be curve B. Now, in terms of figuring out which one's X and which one's Y, you can think of it in terms of just watching the arrows. So if you're at 0, 0, you're increasing both X and Y for a while, but X is increasing much longer than Y is. Y starts to decrease once you get to about right here. Y starts to decrease. So Y decreases before X does. You can tell that pretty clearly here. And so this Y is decreasing. It gets a negative value, decreases faster than the X does. And so that's how I knew which one was X and which one was Y. That's what I looked at. You could have looked at something different, but this top component curve should be the X component, and the bottom component curve here should be the Y component. Now, if you look at curve B, you can tell that these pass through the point 0, -2. Both of them pass through 0, -2. So that's how I knew 0, -2 was a point on the curve, which means that we do have the correct trajectory here for curve B. Now, in terms of the components here, you're not going to tell much by looking at positive time. You're going to have to think about what happens at negative time. So think about what happens when you come out of the point 0, -2. So if you come out of the point 0, -2, then you're looking at what happens going back in this direction. What you notice is, so we always think of this from left to right. Going from left to right, or actually following the arrows is forward in time, excuse me. Following the arrows is forward in time. So forward in time, both of these things are decreasing. But if you go backwards in time, so you think about going backwards in time here, you can actually see that at no point, so here are the Y values, at no point do the Y values become positive, right? I don't actually get above Y equal to 0. So my X values are mostly positive, right? Going back in time, my X values are mostly positive, but my Y values are mostly negative. So you can see that the X values going back in time are mostly positive, whereas the Y values going back in time are all negative in this case. So negative Y values, positive X values once we go back in time a little bit further. So that's how you can tell that the top curve is X and the bottom curve is Y. Now, in terms of scoring this problem, it's worth 4 points. So I would say give yourself 2 points if you correctly identified which one goes with curve A and which one goes with curve B. And then give yourself a half a point for each correctly identified component. And that'll add up to 4. So half a point for each correctly identified component, and then 2 points for correctly identifying the curves. All right, finally on to the last question here. You're looking at what we call a partially decoupled system. So notice that Y does not depend on X at all. And what I wanted you to do is actually solve this system. And the way we talked about this in class, the way that you would go about solving a partially decoupled system is you would solve for Y first, plug it in to the Y here, and then solve for X. So that's what I did. I solved for Y first. It was pretty easy to do that. So dy dt equal -y. This is separable. I know I'm passing through 1, 1, so Y of 0 is 1. And Y of t is e to the -t. So there's my solution for the Y component. If I then plug Y in right here, I get dx dt equal 2x plus e to the -t. So this is a linear differential equation, which means you should have used integrating factor to do this. So subtract the 2x over, set it up in standard form, and then apply the integrating factor e to the -2t. And once you solve for x of t, you'll get this answer. You know that you're passing through x equal to 1 again. So x of 0 equal 1 will allow you to solve for this constant c, which gives you your final answer. And I wrote the final answer as a parametric curve, right? So it's a moving point. This is the x value of the point over time, and this is the y value of the point over time. So here's what I would suggest. This is worth 2 points. I would suggest you give yourself 1 point of credit if you correctly identified the y coordinate, and another point of credit if you correctly identified the x coordinate. So 2 points on that problem. This is something that you might have to do on this next test. So make sure that you understand how to solve by hand these partially decoupled systems. All right, I'll upload the answer key for y'all online so that you have access to that. Take a look at it, make sure that it makes sense to you, and then we'll talk about it later. All right, I want to shift gears now and talk about harmonic oscillators. So if you recall, we were looking at this harmonic oscillator last time. We talked about the derivation of the model and kind of some things that go into it. I want to analyze the model a little bit more deeply today, and then we'll call it a day. So just as a reminder, we were looking at kind of where we left off last time. We were looking at a situation where I have a spring and I have a mass that's connected to the end of the spring. I have a sort of little cylinder component here, which has a dampener attached to it that dampens the motion of the mass. We use C for the damping coefficient, K for the stiffness, M for the mass. And we talked about the potential that there were external forces. In the case of a spring hanging vertically like this, the external force would be gravity. But what we were able to do last time is say that under these conditions, then I could model this particular problem where y, so here is, if I call this equilibrium, y equals 0 is considered to be equilibrium, so that y is measuring displacement from equilibrium. So y of t is displacement from equilibrium. Then the spring mass model is my double prime plus cy prime plus ky equal to this external force. So this is what we called our spring mass model last time. And we did an example last time where there was no damping. So if C is equal to 0 and there is no damping, then the model that you end up with is my double prime plus ky equal to, and I'm going to assume that there's no external force. In fact, we'll be assuming that all the way up until the third unit of the course. But I have my double prime plus ky equal to 0, which gives me y double prime plus k over m y equal to 0. And I mentioned in class that oftentimes what you would want to do is replace this k over m with omega naught squared. This was the oscillator form from last time. So that means going from here to here that I'm letting omega naught be the square root of k over m. And we actually looked at a problem like this in class last time. We looked at y double prime plus 100y equal to 0. And we found that this thing had solution given to us by a constant multiple of, or a linear combination, excuse me, of sine and cosine. And the importance of the 10 here is that 10 is omega naught. So for this problem, you can look here on our model, omega naught squared is 100, which means omega naught is 10. And we talked about last time that omega naught is what we call the angular frequency. It's measured in radians per second. At least for the example we looked at in class, it was measured in 10 radians per second. And what I mentioned at the end of class was anytime you have no damping like that particular example, then you have what's called simple harmonic motion. And what I want to talk about today are the effects of adding in some sort of damping force. So this is if there's no damping. So the immediate question is, how is the analysis different if C does not equal 0, i.e. there is a damping force present? Well, the answer to that question is sort of nuanced because it depends on how much of a damping force is present. The more damping there is, the faster the oscillations in the model are going to disappear. So what we're going to do today is assume a small amount of damping. And when I say small, I mean small enough to allow some oscillation. Now, we're going to make this much more rigorous mathematically later in the course, like how much is too much damping, how much is not enough. But today I'm going to consider the situation where you have a little bit of damping, enough to where this thing doesn't oscillate back and forth forever because that's not realistically feasible, but just enough damping to bring eventually the mass to a standstill. Eventually the mass will reach some sort of equilibrium state. And what's going to end up happening here is eventually y of t, the displacement, will tend to 0 as t goes to infinity. We call this decay. So eventually the oscillation is going to decay. Well, what that means for us is we need to figure out how long it takes for the oscillation to essentially go away, like the amount of time that's involved in decaying. So I have a little table here to show you. So we're going to talk about something today that's called the time constant, tau. Basically, we're looking at transients, okay, because we're looking at homogeneous systems. There's no external force. So whatever solution we produce today is simply a response to the initial condition. You know, we've pulled the spring in one direction and let it go. Its path that it takes from then on is completely dependent on that initial condition that we applied to the spring. There's no external force here. So these are all transients that we're talking about today. And the idea is that the transient, right, is the way that the system responds before it has time to sort of go away. And the damping is what causes the transient to go away. Just like a resistor is what causes the voltage to eventually go away, right? It damps the voltage or damps the current in a circuit. The word transient means short-lived. That's literally why the word transient is used to describe these solutions. What we want to try to ascertain today is how short-lived is short-lived. And that's something that's called the time constant. So all of these examples, the example today that we're going to look at, you're going to end up with decaying exponentials in our solutions. And it's those decaying exponentials that are causing the oscillations to eventually damp out. And so if you think about e to the minus t over tau, for different values of tau and different values of t, you can see how much decay you get, right? So for example, if I let t be 0, then you have e to the 0, which is just 1 times 100%, you get 100% still there. So at time 0, 100% of the energy in the wave is still there. That's how you can think of this. Technically, I'm talking about the amplitude of the wave, but the amplitude of a wave is related to the energy that the wave contains. If I let t be tau, so if I let 1 tau unit pass, you get tau divided by tau, which is e to the minus 1. And e to the minus 1, that number, when converted to a percentage, is 36.78%. Which means that after 1 tau unit has passed, we've reduced the amount of energy in the wave by 64%, but there's still a good amount of energy left here. Similarly, if you keep stepping tau at a time, you eventually reach what we call 5 tau. So 5 tau is 5 time constant steps, and it's generally agreed that once you've gone to 5 tau, there's so little energy left in the system that we can basically ignore the transient at that point. And if there are any external forces, look at the steady state that comes from those external forces. So we've essentially, in the time span from 0 to 5 tau, virtually reduced all of the amplitude of the original wave, the transient wave that's in the system. So what I want to do with this is take a look at what happens in our solutions. Our solutions are going to contain exponential terms of the form e to the minus pt. And remember, tau was what we divided by t. So tau is going to be the reciprocal of whatever the number is that's in front of t in the decaying exponential. So if this is e to the minus 7t, then tau is 1/7, okay? The best way to think about this is to just do it and look at an example of it. So suppose that I was to solve a spring mass system and this ended up being my solution. So eventually you can see that we've got, you know, two exponential functions that are decays. They're going to decay away, which is eventually going to leave us with a steady state of 15. But what I want to know is how long does it take for these terms to essentially go away, to die off, okay? So I want you to sort of pause the video here and see if you can figure this out. Use the time constant. Remember, you got to go out to 5 tau. Use the time constant in order to figure out how long it takes for the transients to die away. So 5 tau is that point. So pause the video at this point. And if you haven't paused it yet, just hold on. We're going to take a look at it together. All right. So the example that's here is we're looking at, this isn't an oscillation, but this is the kind of solution that you can get out of this spring mass model when there's too much damping. You get just straight decay. So this is something that could come out of our spring mass model. What I'm looking at here is you've got e to the negative 2t and e to the minus 5t. So I know that e to the minus t over tau is what I'm looking at. But if I want to use instead e to the minus pt and look at that, which mostly that's how we write things, then it turns out the relationship here is tau is 1 over p. Okay, so because of that, this is what I'm looking at here. The p-value for this exponential is 2, and the p-value for this exponential is 5, which means that the tau value here is 1/2, and the tau value here is 1/5. Now the question is, what does that tell me? Well, after 5 tau, so after t is 5 tau, the solution is sufficiently damped out. So 5 tau would be 5 times, in the case of this one, I'll call this tau 1, I'll call this tau 2. 5 tau 1 would be 5 times 1/2, or 2.5, and this would be, the units here would be seconds, okay? So it's going to take, well, the units don't have to be seconds, but in the problem, I'm telling you the units for time are seconds. So it's going to take approximately 2.5 seconds for that first exponential to damp out or decay out. It's going to take the second exponential, it has a tau of 1/5, it's going to take it approximately 1 second because it's a faster decay. It's a e to the minus 5t instead of an e to the minus 2t. It's a faster decay, so it's going to take it about 1 second to damp out. But both need to disappear in order for the entire solution to damp out. So both of these terms need to go away. So I need the larger of these two values. So the whole thing, so the whole solution damps out after approximately 2.5 seconds. So that's the answer that you should have had on this particular question is answer choice C, the transient dies out after 2.5 seconds. Let's take a look at that because I want you to see it in Maple, exactly what it is that I'm talking about here. If I was to just plot that solution real quick, so the solution that we have there is for, let's see, e to the minus 2t minus 3e to the minus 5t, excuse me, plus 15. And here's one of the main reasons why I'm doing this with you is, you know, at this point I would want to plot I would want to give Maple the time interval. In other words, t goes from time 0 up to some value. And the question is, how long should I let this play out? Well, I know that most of the decay is going to happen in the first 2.5 seconds. So I need to go at least 2.5 seconds, probably 3 or 4, so I can see the steady state part take over. So I'm going to go out to, let's just go out to 5 and see what it looks like. So you can see here the solution that we have. After 2.5 seconds, this thing is basically right at 15. And we can see this a lot better if I kept my y values here. Let's go y equal, I don't know, 14.5 to 15.5. Right? So after 2.5 seconds, right, virtually all of this wiggle that's in it, that's coming from the exponentials is gone, and this thing just flattens out after that and is a steady 15. So most of the decay is gone after 2.5 seconds. We're going to look at an example that has a true oscillation coming up in just a second, but I just want to make sure that we're understanding how we can calculate these things. So if I ask questions on an exam or on Maple Lab that say about how long does it take for the oscillations to die out, this is the analysis that you're being expected to use on that. All right, so let's talk about what happens if we have a little bit of oscillation. So this is harmonic motion with a small amount of damping. And once again, we'll classify later in the course what a small amount of damping is. Well, we know that if it's just simple harmonic motion, we know that y of t is some constant, I'll say a times cosine omega t plus some b times sine omega t. We saw that in class together. All the damping is going to do is our solutions are going to have a term like e to the minus pt, a decaying exponential out in front. And what that does is that reduces the overall amplitude of the wave. We know that from our conversation in class on Monday, that anytime you have a wave that has the same frequency, omega here is the frequency, that I can rewrite this as some value, I'll say d times cosine omega t minus phi, right? So I can write this as a single wave. And this is where d is the amplitude of the standing wave. And that amplitude can be calculated by taking the square root of a squared plus b squared. So we talked about that in class. We also talked about the phase lag phi in class. And what I said in class was that the phase lag is the tangent inverse of b over a in this case. So there's a couple of things that we need to talk about what does this function look like. So the e to the minus pt is where the damping comes from in the problem. And based on the analysis we just did, we can consider this thing damped out after 5 tau. So after t is equal to 5 tau, which remember tau is the inverse of p, so it damps out after 5 over p, whatever that value of p is. Now we're going to figure out how to find the value of P very quickly in future examples, but there's more to say here. You know, omega is the angular frequency, which is typically measured in radians per unit time, or radians per second, radians per minute, whatever the case may be. But there's another measurement of omega that we typically will want to deal with, and that is thinking of omega as being 2 pi times f. And it's this frequency f that I'm really interested in, because f is called the Hertz frequency. Sometimes we call it the natural frequency. Because if you think about what f is, or omega is in terms of radians per second. So f would be omega divided by 2 pi. So f would equal omega divided by 2 pi, which the units of omega are radians per second, but I'm dividing by 2 pi, which is clearly a radian measure. So the radians go away and I end up with inverse time. And it's not really inverse time because that one that's left, I really think of this as a cycle around the unit circle, or a cycle, one complete oscillation of the curve. So over time, the unit hertz, we really want to think of this as cycles per second. So this is the unit hertz that we'll be dealing with a lot there. You then want to talk about things like periods. So the period of the oscillation. So the period of the oscillation is the time it takes to complete one full oscillation. So you can think of this as time per cycle, right? So the time it takes to complete one full cycle. So oscillation, having trouble spelling here this morning. So one full oscillation, or one full, I'll say one full cycle. So this is actually, we call period, we usually use capital T for that. All this is it's the inverse of the Hertz frequency, because you can see that Hertz is cycles per second. So how many seconds for one cycle, right? How many seconds for one cycle is literally the definition of period. So it's the inverse of the Hertz frequency, or you can take 2 pi over omega if you want to write it in terms of angular frequency. All right. What I want to come back to on this is back to how the solution is going to look here when we have a small amount of damping. What you actually end up with here is a wave. So you get dE to the minus pt times cosine omega t minus phi. This part is going to give the wave-like structure. It's going to give the oscillation. And this part is what's actually controlling the amplitude or the energy associated with that oscillation over time. So this function right here is a decaying exponential. So over time, the amplitudes of the wave are going to decay exponentially. And so we give a special name to everything that's happening here. Because the amplitudes are decaying, it's not just a straight frequency. It's not just a straight period. So we say dE to the minus pt. This is the time varying amplitude. So the amplitude of the wave will change over time. And these are typically called envelope curves. And I'll show you an example in Maple here in just a second that'll kind of drive home why that envelope curve term is appropriate. And because of that, anytime you're dealing with a problem that involves damping, you don't have true simple harmonic motion. You don't have true periodicity, because as you complete cycles, the cycles get smaller in amplitude. So we don't use the term period anymore, because period refers to a pure oscillation. We use the term pseudo period. You have a pseudo period of this oscillation. We don't use the term angular frequency. We say angular pseudo frequency, or Hertz frequency, or natural pseudo frequency, because it's not a true cosine or sine wave whose amplitude never changes. So if you see in Maple or read about pseudo frequencies, what I'm talking about is a wave that has a frequency, but the wave's amplitude is decaying over time. So it doesn't make sense to call it the frequency doesn't change, but the amplitude does. So it doesn't make sense to refer to it as just a true period or a true frequency. All right, so let's take a look at a problem here that's related to these concepts and see how we do. So here's the problem. Suppose that we have a solution to our spring mass damper system, and it's given to us by this particular equation. What I would like to know is how many complete oscillations will occur before the transient response has disappeared. So how long does it take it for this to essentially die out? How long does it take it for this solution to die out? So take a second, pause the video here if you need to consider kind of what will happen here. And then we'll talk about it together on the other side. All right, so if you haven't paused yet, please go ahead and do so. All right, so the example that I'm looking at here is y of t equal e to the minus 0.2t, 3 cosine 10t plus 2 sine 10t. I just want to do a bunch of analysis here, and then we'll try to actually answer the question that's being asked. So my first piece of analysis is I want to write it in that single wave form, right? So I've got e to the minus 0.2t. I'm going to combine the amplitude of this wave. It's going to be the square root of 3 squared plus 2 squared times cosine of 10t minus phi. Now I'm not super interested in phi. I'll show you where you can see phi in the graph here in just a second. But you know, we can calculate that as well. So that would be tangent inverse of 2 over 3. Let me go ahead and get a value for that. So that's around 0.588. All right. Let's see. 3 squared is 9 plus 4, so that's square root of 13. E to the minus 0.2t. Cosine 10t minus phi. So this is what the solution to this problem looks like. It looks like a wave that has an angular frequency of 10. There's a little bit of a lag. The lag is going to be 0.5 divided by 10. So we'll look at what this number looks like in the graph here in just a second. But there's going to be a little bit of a lag. You're going to have a decaying amplitude. Initially, the amplitude is going to start out at square root of 13. So let's see, square root of 13 is somewhere between 3 and 4. So our amplitude will start out somewhere between 3 and 4. And then over time, it'll decay to 0 because I do have some damping in the form of this exponential. So the question is asking, how long does it take before the transient response has disappeared? So looking at this, I know that P is 0.2, which means that tau is 1 divided by 0.2, or tau is 5. So because tau is 5, I know that 5 tau, which is 5 times 5, or 25 seconds, is how long it's going to take for this thing to essentially damp out. So after 25 seconds, this oscillation, most of the transient response will be gone, and it'll be effectively damped out. It'll be effectively 0. So what I need to do to answer the question, though, is figure out how many oscillations are going to occur in that time. So in order to figure that out, I need to think about the period. The period of this oscillation is 2 pi divided by the angular frequency, which is 10. So that's what, pi fifths, which is about 0.628. So this is this many seconds to complete one cycle. That's what this number tells me. So I've got 25 seconds. I can multiply that, or I can divide, excuse me, I can take 25 and divide by 0.628 to get the number of cycles. So the number of cycles that this thing would complete is equal to 25 divided by 0.628. This number is approximately 40. So there are approximately 40 oscillations that occur in 25 seconds for this wave. Let's take a look at this in Maple and see if we're correct. All right, so the wave here is, I'm going to plot e to the minus 0.2 times t times 3 cosine of 10t plus 2 sine of 10t. And we'll plot this for, we said it damps out after 25 seconds, so I'll plot it for 30 seconds. Need an extra parenthesis, there we go. So you can see here that we have a view of this wave and the oscillations that occur. You also have this function, which looks like an exponential, which is governing the top, and another one which is governing the bottom. And I'm going to talk about that in just a second. But it looks like that by 25 seconds of time, we should have 40 oscillations. So let's count the peaks. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, and number 40 happens right at the 25-second mark. So there's the 25-second mark and there's number 40. So there are approximately 40 oscillations that occur before this thing's energy has sufficiently damped out to the point where it's essentially zero. There's very little energy, very little amplitude that's left in the curve at this point. So what I want to go back to now is the, when we wrote it down together, we wrote, let me bring this back over. We wrote that I could write it in this form, and this guy right here, which we called the envelope curves, turn out to be very important. And I'll show you what these curves represent on the graph here in just a second. So I want to plot this function, right? I want to plot this function against that oscillation that we have. So this function is square root of 13 times exp to the minus 0.2t. And I'm going to go ahead and put in the negative of it as well. So I'm going to plot all of these together with that original oscillation. And I'm going to give these different colors. So color. Oh, 0.2, not 2, 0.2. Okay, what you can see here is this envelope curve is literally the curve that governs the peaks of the oscillation. It governs the amplitudes. So that's the importance of these, is we know between plus or minus that envelope curve is where all of the oscillation will be occurring, and it all gets damped down to zero over time. So in your Maple work, if you're asked to plot envelope curves, this is kind of what I'm asking you to do for that particular instance. All right. So on this problem, you should have had 40 complete oscillations. I'm going to give you all credit for any learning catalytics questions that we go over today, because we would have normally gone over them in class, and I don't feel like it's right for you to get points counted off or not be able to earn bonus points because, I'm having to do it this way. So I'll give you credit for the learning catalytics questions that we missed during this time. All right, the last thing that I want to talk about today is kind of an analogy between two models that we've seen so far in the course. And this analogy will play out over time to be more important as we go on. But for right now, I just want to address what it's called and kind of what we've seen so far. So it's something called the mechanical electrical analogy. Essentially, mathematically speaking, two systems are analogous to each other if the systems are modeling two different physical situations, and the differential equations which model those two systems are essentially the same with just different labels. And what we've actually figured out here is that the spring mass equation and the equation which governs the current or voltage in a circuit, or the charge on the capacitor of a circuit, have a relationship with one another. It's called there are different analogies that can be drawn here, but the most common one is what we call the force voltage analogy. If you think about the external force being applied to a mechanical system, that external force we've shown in class is mx double prime plus bx prime plus kx. This is that spring mass equation that we came up together. I think we used C in class, but B is more common. And if you think of an external voltage being applied to an electrical system, this was the equation, the LRC equation that we came up with earlier in the course. You can draw direct parallels between these two equations. For instance, you can say, well, external forces in a mechanical system are like voltage sources in an electrical system. Mathematically, they behave similarly because both of them force the system to do something. The mass of a spring is somehow related to the inductance of a circuit. So the mass of a spring acts like the coil of a circuit. Like physically, they're completely different, but mathematically, they're completely analogous. The frictional damping coefficient B, so this damping coefficient that we have in our spring mass model, it's like the resistance that's in a it's like the resistance in a resistor on an electrical circuit. They behave similarly mathematically. And that should make a lot of sense, right? Because frictional damping is resisting the displacement of the mass, whereas resistance is literally resisting the current or voltage that's traveling through the circuit. And because of that, they behave very similarly mathematically. Finally, if you look at the last piece, the stiffness constant is somehow related to the capacitance. So how much charge it's inversely 1 over C, how much charge you allow to build up on your capacitor, the capacitance, the amount of charge that it can hold, is somehow similar to the stiffness of your spring. It's what keeps this thing from alternating back and forth quickly. Like the stiffer the spring, the less quickly it's going to alternate back and forth. And so, the concept of displacement is the same as the concept of charge, which means that the concept of velocity is the same as the concept of current. Mathematically, there is no difference between these two systems, which is why we're going to spend the entire third unit of the course studying second order differential equations like this, subjected to different forces, because we get a 2-for-1. If we know mathematically how to solve these things, then we know mathematically how a mechanical system reacts and how an electrical system reacts, because they react the same way. There are other analogies that can be drawn. You can draw an analogy between the external forces of a circuit and the current in the circuit. Here, this was between external forces and voltage, but I can draw a connection between force and current. For rotational mechanical systems, there's an analogy between the torque on the system and the voltage that goes through a circuit. So there are many analogies that we can draw between mechanical systems and electrical systems. And we have the benefit in this course of not having to pick favorites. This is a math course, not a physics course. So I don't have to pick favorites here. I can just study the underlying model and figure out how the underlying model behaves, thereby giving me some sense of how the physical real world model behaves. And we're going to do that going forward, especially in Unit 3. All right, I think that's a good stopping place for today. I got most of the stuff done that I wanted to get done with you. This should open you up to being able to finish the Maple Lab, no problem. I do want to say that there is one SIR question, I believe, on the Maple Lab. I'm asking that you just go ahead and read section 2.8 about SIR to be able to try to do that, but it's not gonna hurt me if you want to wait till after we talk about SIR on Monday to finish up your Maple Lab. So technically the Maple Labs are due on Sunday. If you want to go ahead and finish it by Sunday, great. But if you need till Monday to finish that up after we talk about SIR on Monday in class, then that's fine as well. There should be another video that'll pop up on Friday for you over the material that we would have covered Friday during Q&A. And so keep a lookout for that as well. All right, y'all have a good day.